Can we go, so in the free body diagram, is there going to be one diagonal and one parallel like you said? Okay. Say
This.
please.
Okay. So if you look at this question about number 9 with the row, okay? So if the box is just sitting there, what forces do you have?
Force normal and force gravity.
Yeah. You got F, G, F, N, right? Now, unless she's lifting this thing straight up.
Ellie!
Yeah, let's just stop class.
Ellie! Okay, we did. So, unless you're lifting this, I don't care about this, okay? Now, so here's Megan, right? And she's dragging the rope, right?
Yeah.
So, this is not an incline plane problem. We're not dragging this thing up an incline. It's horizontal, and it's like we're dragging this rubber stopper, and it's at an angle like this, okay? So the only force that we consider in terms of the work calculation is this 462 newtons. That's it, nothing else, okay? Because that's only the force in the direction of motion. Now here's the bigger picture. What's the only reason this 462 Newton force exists?
Because she's pulling on the rope.
Well, but why does she have to keep pulling on the rope?
Because there's friction.
Because there's friction. And what's the frictional force? Negative 462 newtons. Because if this didn't exist, this force wouldn't exist, and she wouldn't have to do any work. So she could just go whoop like this, and then just walk, and the box would just keep following like a lost puppy in search of, you know, a dog treat. So here's 462, here's 462, boom, boom, boom. Now, the first question you're asked to find is the tension. That's going to be this side of the triangle. So clearly, if this is 462, what does your tension have to be bigger than? 462. Otherwise, it doesn't even work in non-Euclidean geometry. So I've got this. Here's my tension. Is there a vertical component to it? You don't have to find it, but you need to label it. Okay? Because that's all the components that are acting on that tension. Horizontal component, a vertical component, and then the tension itself. But the only force you consider in your work calculation is this 462. Don't take the tension force because the box isn't sliding like this. Okay? The box is going horizontal, so I only worry about that 462 Newton force. That's it, nothing else. Boom. Now, if you look at question number 10, that changes the problem for spring. So, here's your escalator. Boom. Okay? So there's two ways that you can work this problem if you don't have to worry about friction. And I don't care how you work the problem, you're going to get the same answer. You do the same math, you just change the sequence. So one option is that you look at this and go, okay, here's your FG. So the upward force that has to be applied is overcoming his force parallel. So one option is that you find the force parallel, you multiply that by the length of the escalator. That's option number 1. Okay? Option number 2, because if you're not worrying about friction, the other option is that you take the weight of the president and multiply that by the vertical height that he gets lifted. Okay? Doesn't make any, you're going to get the same answer either way. So either you apply a big force and just lift him straight up, or you apply a smaller force up the entire length of the escalator. It's the same thing. Okay, it is the exact same thing. The only thing you do is you change the sequence. Okay, you'll get the exact same answer either way. It doesn't matter. Okay? Now, if you look on number 11, here's this block. It's going to slide down an inclined plane at a constant velocity. We're not pushing it, we're not pulling it, we're just setting it up here, and it's going to slide down. So, here's the deal. Here's the inclined plane. What forces are acting on the block? Force parallel acting down. So what's the only way that it can slide at a constant velocity? If your force friction is same but opposite. Now, which direction is your frictional force acting? In the same direction as motion or the opposite direction of motion? So anytime your force is in the opposite direction of motion, that's defined as having a negative value. Okay? Got that? Beautiful. Now, let's talk about number 12. And this is what I showed on Monday. So, you have unequal mass. A and B both have the same amount of force. Mass A is larger than mass B. So here's A, here's B. Okay? And they're both, say, hooked up to pulleys, and you have the same mass suspended from the end. Okay? So one of two things is going to happen. Either you're going to have the same force acting over the same time, or you're going to have the same force acting over the same distance. They are completely different ideas. Okay? They are completely different ideas. But here's the one thing that's going to be common. Are both objects, A and B, going to accelerate?
Yes.
Yes. Is the acceleration going to be the same? No. Which one's going to have the larger acceleration?
B.
B is. So when you look at this, you got, oh, okay, same force. So if this is B, it's got a small mass, so it's going to have a large acceleration. A is going to have a larger mass, so it's going to have a smaller acceleration. Start with that idea. So when you look at this, what's going to happen? Okay, how much work is done? Excuse me, wrong one. We're trying to travel further. Explain. Now, here's what I don't want. Do not tell me, oh, B is going to travel further because it has less mass. Bad. Wrong. No. Bad. Okay? That is not enough justification. You need to talk about acceleration, but what is common to both of them?
They have the same force applied.
They have the same force applied. That's going to affect their acceleration. But what else is common beyond the same force?
They both have the same
Time.
Doesn't matter. Coefficient of friction. Doesn't matter.
Why?
Because they're going to end up with the same acceleration. So, what else is the same?
Time.
Time, right? Now, in terms of this, you could look and say, oh, A equals V minus V naught over time. So, you need to talk about, if you're talking about a velocity, which one's going to have a larger velocity? Talk about this. Oh, one's going to have a larger acceleration at the same time, it's going to end up going faster. Or, if you want to talk about distance, you can look at, oh, distance traveled is 1/2 AT squared plus V naught time. Both of them have the same initial velocity of 0. Since time is the same, the one with the larger acceleration will travel with a greater distance. But just don't tell me, oh, the one with the larger acceleration. That's not enough. Because I can have Grandma accelerate very, very slowly, and you accelerate very, very quickly, but Grandma can still end up going faster than you do if she accelerates longer. So just because something has a larger acceleration doesn't necessarily mean that it goes faster. Okay? Because you have to look at how long that acceleration is going to take place. So that's why you just can't say, oh, that has a larger acceleration. That isn't enough information. If you explain it in terms of time, then that becomes a valid explanation. Okay? So just saying, well, it's got a bigger acceleration. Well, great. You know, Topeka is the capital of Kansas. That's really not relevant either to the discussion.
That is correct, though.
It is correct.
So you can't count points off. Okay.
By the way, if you're out tonight, there is what we call a super moon. Okay?
I thought that
Well,
was
it's
yesterday.
basically both nights. There isn't going to be that much.
That was next week, so.
And this basically won't happen again for another 18 years until some of you are like 36. Okay? By that point, you might have kids that are in high school.
That's creepy.
I'm just telling you.
Ew.
I'm just telling you, it could happen. I'm not saying it's done. I'm just saying in 18 years, some of you could very well have kids that are in high school, maybe freshmen, but it could happen. I don't recommend it,
Nope.
but I'm just saying it could happen.
Nope. Yeah, no.
And you can say,
Wrong.
man, last time that happened, I was in Mr. Burkham's physics class.
Mr. Physics Burkamp.
That too. Okay? So, anyway, so if you're out tonight, especially if you get like a pair of binoculars, it's really cool to look at. Anyway.
Will they both have the same
Mr. Burkamp's Physics. Mr. No, dang it, I said it right. Mr. Physics Burkamp.
Okay. When you get to number 8, and I dinked this up because I inserted the question and I forgot to go back and change the sequence. But D is referring to, when I ask on D, it says, explain the similarities, differences in your answers. That should be between B and C, not between C and D, because D is the question. So that should be between B and C. Okay? And when I talk about similarities and differences, I want both addressed. What's the same on B and C? What's different between C and D? Now remember, power is work divided by time, and you'll see this today, but power is also change in energy per unit of time, but no matter what, it's joules per second, which is also watts. Okay? Anything else? Once, twice. So here's the next big thing, and this is this idea of energy. So if you look at what energy is, it's actually become one of the most important topics in whether it's politics, whether it's discussions about the world economy, whatever. And everybody knows what energy is. As a matter of fact, like when you all walk in, I can pretty much give you, like just looking at how you walk in, what your energy scale is on a scale of like 1 to 10, you know. Reese walks in and he's like, how you doing? You know, it's like, oh, Reese is about a 2 or 3 versus Reese walking in, oh my God, ah! Okay, all right, Reese is about a 10, you know. So you all know when you have energy and you know when you don't have energy. People can just watch and go, oh, okay, right, this is how much energy that you have, you know. Meat tends to be at a pretty level, you know, 4 or 5, pretty consistent right there. So
I'm usually about.
no, you're a fluctuator, okay? You're a fluctuator. Yeah. Woo! All right. So, but if I said, what's a definition of energy? If I said, okay, I want a one-sentence definition of what energy is. You just got back from the journalism conference. You were a purveyor of words.
A purveyor of words.
Yes. So what would you say if I said, you're writing a story for Newsbag, I want a definition of energy. What would you say?
The amount of
The amount of
words. More words. I don't know. The words are escaping me right now.
That was, I don't remember.
It's the amount of blank.
Writer's block.
Writer's block. I'm having writer's block. The amount of energy. That's it.
So you're using energy.
What is going on?
She's had hiccups.
The amount of energy is the amount of energy?
Yep.
Okay.
It's not false.
All right. Well, it kind of is. So the simple definition of energy from the physics perspective is energy is the ability to do work. Okay? So, and it plays out, so let's say that it's 6 o'clock on a Saturday morning, and Aunt Martha is coming over for breakfast at 8. And your mom realizes, wow, the house is a disaster, you know, Aunt Martha's a bit British. So, your mom wants the house to be clean so that she doesn't get the Aunt Martha scowl or evil eye. Okay? So she comes to you at 6 o'clock on a Saturday morning and says, hey, Skippy, get out of bed. I need you to run the vacuum cleaner. And you say, oh, I don't have the energy. Okay? Now, from a physicist perspective, physicists in the world go, okay, we understand that. Because what we're saying is that you do not have the capacity to annoy me. You're saying that you do not have the capacity to do work, to take your arm and exert a force through a distance to run the vacuum cleaner. I don't have energy. I do not have the capacity to do work. And Mom says, tough, I've got more energy to kick your butt if you don't get out of bed, now do it, okay? But I'm just saying, so Mom's energy trumps your energy on a situation like that. So, if you go to the gas station, you pull up the Quick Trip, buy gasoline, fundamentally, what are you buying?
Energy.
You're buying energy. You're buying energy and the capacity for your engine to do work, to exert a force through a distance to drive the pistons to move your car down the road. You have lunch. Why?
Because you
It's
need
about the
energy.
energy.
You need energy.
Because the
Calories.
mitochondria is the powerhouse of the cell.
That's not even a science.
Okay, it is. But,
Dude, it's not even freaking relevant.
It's not physics, it's not physics.
okay.
Even freaking math.
So, when you look at this idea of energy, and if you look at from an economic standpoint, okay, so let me kind of give you a historical perspective. So, if you look at challenges that have faced different generations, okay, my father was born in 1927 by what is now Cheney Lake. 1927, when he was growing up, 21st Street was literally a set of wagon ruts. That's all 21st Street was a set of wagon ruts. So when they would come into town, they would literally hook the horses up to the wagon, and they would come into town on a wagon. So Dad died in '96. So if you look at the changes that my father saw during that time, so he went from riding into town on a wagon pulled by horses, and 21st Street was a set of wagon ruts, to flight, to space travel, where it became routine. So my father saw a tremendous change in transportation from the time that he was born until the time that he passed away. From horses all the way up to space travel, going to the moon, where it was just became mundane, wasn't even a big deal anymore. So my generation has seen a change in transportation. Excuse me, not transportation, communication. So when I was little, grew up out of Cheney, lived out in the country, and we had what was known as the party line. Anybody know what the party line was? Okay?
That sounds cool.
No. So when you had a phone, because the phone systems then were relatively new, so you might have 3 or 4 houses that were all on what they called the party line. So you'd have to pick up the phone, which was attached to the wall. I realize that's a radical concept. It was attached to the wall, and you'd have to listen to make sure nobody else was talking on the line. Because if it was, you couldn't dial. So now if you wanted to be a snoop, you could listen in on somebody's conversation. But you had to keep, but you always had to keep that in mind. Now, so you always had to be cognizant of what you were saying, because you didn't know who else might be listening in on it. So if you were a kid, a teenager, I mean, okay, number one, there was no cell phones. And you talk about, oh, I need my privacy. Okay, you didn't even have privacy in your conversations, because number one, the other 3 neighbors might be listening in, and the only phone in the house is right there in the living room where everybody and their dog could hear what you were saying. So the idea of privacy and communication did not exist.
So trying to smooch up on some ladies.
Yeah, not recommended.
Were the Polaroid pictures around?
Yeah. They did have Polaroid pictures. Not recommended.
Color?
Instagram. Yeah. Okay.
Shake it.
So then, if you were uptown, you had a private line where you had to pay extra, but nobody else could listen in on your conversations. So you have the private line, you have the party line. So this was in the time that we refer to as BC, which is before cell phones. Okay? Stunning. So cell phones came out, but before cell phones came out, basically you were limited on battery storage. So all the cell phones were these big, massive bag phones. And the only time they would work is if they were plugged into like the cigarette lighter in your car or plugged into an outlet. They were cool, but they really weren't mobile. They were mobile in the sense that you could have them out in the car and you could have them plugged in. So then they said, okay, well, the batteries got a little bit better, and then then you had cell phones about the size of this cup, right? And those were cool. So if you look at the old movies that came out early 80s, mid-late 80s, 90s, you see people talking on these cell phones like they're massive. And then the batteries got better, and the transistors got better, and you improved the technology, and now you have cell phones, like this. And so if you look at what I've seen in terms of changes in communication, my generation has seen a complete revolution in terms of how you communicate. I was in high school, there's no idea of texting or cell phones or Facebook or Snapchat or whatever it was, okay? Didn't exist. I mean, you made a phone call. And so, as a matter of fact, one of my nieces sent me a deal over the weekend. It was like, you guys were referred to as millennials. It was like millennial merit badges. And like you get a merit badge if you actually talk on the phone to someone that does not involve in ordering takeout food. You get a merit badge, okay?
I read the other day that like every day now more data is like transferred and like stored than from the beginning of time up until like 1991.
Oh, I have no doubt.
Every day.
I mean, seriously, you guys on your phones now can literally access the Library of Congress. Whereas, even like when I was in high school in the mid-'80s, you wanted to do research paper, you had to go to the library, actually get books off the shelf. Stunning. I know, it was stunning. And you had to look through actual magazines. And if the library didn't have the magazine, you were screwed. Because you could only access what was in print. So, my generation, it's all about communication. So here's what I think will challenge your generation, and that's energy, okay? Availability of it and cheap energy. So here's the problem.
Here's the solution.
No. Here's the problem. Yes, gas prices right now are cheap. If 3 or 4 years ago, I would have bet you large sums of money that gas would never get below $2 a gallon. I honestly remember thinking.
I remember it was like he was 5.
Yeah, I said I will never see gas below $2 a gallon in my lifetime. Supply and demand curve.
It's like 189.
They're producing oil. What's going out of style? Prices drop. Boom. Here you go. So, but here's the problem with the production of large amounts of fossil fuels. Every time you burn something, you emit carbon dioxide. So they just announced today, pretty much guaranteed that 2016 will be the warmest on record since they basically started keeping track of records, which would just pass 2015, which was now going to be the second warmest temperature ever recorded. So, great. Cheap fuel is great, okay? It fuels our economy. Because think about this. Let's say, hypothetically, overnight the price of gas goes to, I don't know, $6 a gallon. You wake up tomorrow morning, gas is $6 a gallon.
I'm walking.
You're walking. Or if you continue to drive, your disposable income drops like a rock. How much food is growing in the store at Dillon's? None of it. It's all shipped there. All of it is shipped there, or at least processed there. So look what that would do to the cost of food. Look what that would do to your ability to go to movies, rent movies, be entertained. Drop like a rock. Okay? Your disposable income, your parents to buy food, to feed you. Look what it would cost the price of transportation here at school. It would wreck the economy. Think about this. One possible idea is that we have all of these communication satellites. It's a cool deal. Works like a champ. But in years past, we've had what's called a massive solar ejection. That happens, basically, if that happens again, these communication satellites can be toast. Guess what happens to the internet? Gone. Worst case scenario, you also fry the electrical grid. Worst case scenario that I've seen is that basically we lose electricity for about a year. So imagine you going a year without electricity, without cell phones.
What are the chances of this?
Pretty slim. But it happened in like the 1880s.
Give me an ish. Like a point.
Around your
Yeah.
first teenage birthday. That would be bad.
But here's what happened. I mean, it was back then we had the telegraph system, okay, which was a series of cables. And there was so much energy produced from the sun that it fried, literally, it toasted those cables. So even that simple communication system was destroyed because of this large amount of energy that comes from the sun. So I'm not saying it's going to happen, but I'm just saying imagine the possibility. Look at how your life hinges on the ability to store, it isn't up here, but a different type of energy that's vital to your life, what we call EWI, electrical potential energy. Imagine if you didn't have batteries, and the only time your cell phone could work is if it was plugged into the wall. Ooh.
I'd have
So, think about your car. Anybody know how the first generation of cars were started?
They plugged them in.
No.
Or no, didn't they
Wasn't there a
like?
crank on the front?
There was a crank on the front. Okay? There was a crank on the front, and that's how you would start the engine. Because they didn't have good enough batteries to store electrical potential energy.
Well, I know there's one at Davis Moore. We have like a 70 Cadillac there right now, and it has to be plugged in all the time.
Yeah, but this one, like it was literally, there were no batteries. You had to crank the engine to start it. So here's my point: your existence, and basically everyone's existence, hinges on the availability of electricity and the ability to store that electricity, a very readily supply of that electricity, and the same thing with fuel. So, but here's the trade-off. You look at the carbon dioxide emissions, okay? Carbon dioxide in the atmosphere has climbed like a rock, and you can argue all you want, well, the models are off and it's temperature change. No, not buying it, okay? You can just look at what's happening to the acidity of the oceans. Carbon dioxide is being absorbed by the oceans are becoming much more acidic. It's destroying the ability of clams and oysters to make their shells. That's going to collapse the bottom of the food chain. You collapse the bottom of the food chain, everything else is going to be screwed further on up. And so, when I look at what I did,
really freaking me out right now.
I'm just telling you.
Is there like,
This isn't zoology.
Why don't I see
No, but I'm just
why
telling
don't
you.
I see this on the news?
Because the mainstream media doesn't want it.
Energy like
It's not going to happen.
use
Okay,
like
either
fossil
the sun
fuels.
going out.
Okay, well, let's talk. So,
No, it couldn't.
I know.
so like here, literally, up to until about last March, I drove a best truck I've ever owned. It was a 1500 Dodge, had a V6 in it, got like 16 miles to the gallon. Okay? And I love the truck. I love four-wheel drive, bright red. Oh, love the truck.
You looking for a new one?
No.
You sure?
No, trust me.
I got it.
I'm sure you do. But, so, basically, every time you burn a gallon of gasoline, every gallon of gasoline that you burn, you kick out about 20 pounds of carbon dioxide for every gallon of gasoline that you burn. Okay?
Why is NASCAR still a sport?
I don't know.
Yeah, honestly.
Well, but because it's money, that's why. And so, I traded the truck in, I got a little Mazda 3 that gets about 40 miles to the gallon. And so, I figured that difference in mileage and what I drive in a year is a difference. Now, this is just me. That's a difference in tonnage of carbon dioxide of about 6 tons a year between driving that truck versus driving that car.
Do you still have a truck?
No, I traded it in on the car. Okay? I've still got another truck that I use on the car.
You
But this
for a
was just
Bolt?
commuting back and forth to school.
I bet you'd like a Bolt, huh?
No,
How far is the drive?
they're ugly.
Dude, they are quick though.
I don't
was
care.
really
Okay.
surprised.
How far is the drive?
It's about 18 miles. So then this summer, had solar panels installed on my roof of my shed. So,
How
yeah.
much money are you making right now? 'Cause you seem like
That's not a question that you ask.
Yeah.
Okay, well, I don't have a lot of social awareness. I really don't.
So, and everybody says, well, that's just a drop in the ocean when you look at all the other sources of carbon dioxide that's being emitted. And you're right, it is. It's a drop in the ocean. But it's my drop in the ocean that I've chose to take out of that production. In terms of
just
carbon
you're
dioxide.
That's just
No, but here's the point. And everybody says, well, it's not going to make any difference. But if you have enough people making that difference, then you start to see change. Okay? So, and because I could not, in good conscience, continue to drive that truck back and forth to school just because I like driving that truck. I couldn't do it. I was like, okay, I got to do something to lessen that. And you consider, okay, that's 6 tons a year. Okay? So it makes a difference.
Wait, how much were you paying for gas? Because I drive 30 minutes to school every day, and I fill up on gas twice a week, and I drive a Honda Accord. So you had to be, and if you're,
It wasn't the cost, it was the carbon dioxide.
I know, but like still,
Yeah,
like,
it
if you're driving
wasn't-
a truck
so
that's getting 16 miles per gallon, you must have been getting gas all the time.
Yeah, I was. About once a week I was.
Yeah.
So what's a smart
Yeah.
car get?
Okay, so when you talk about energy, and we all need it, we have a society that's built on it.
Like,
There's two broad, very broad classifications of energy.
in my work.
Potential, which is, and we're going to talk about all of these. So you can have potential energy stored in a spring, like if you pull back a spring or compress a spring. Gravitational, this is one we're going to deal with first, which is MGH, okay? On the kinetic side, you basically only have two types. You have translational, and then you have rotational. Well, that kind of falls under the potential side, which is like, you can also over here, like how your cell phone works is buoy, which is electrical potential energy. So your cell phone, your car starts because of buoy. We'll take AP physics, we can do that in the spring. So these are the two big ones that we're going to deal with. These are the two that we're going to deal with over here. So let's talk about these two. So when you look at translational, that's 1/2 mv squared, and rotational is 1/2 I omega squared. So if you look at what they have in common, this is, they both have a half. This is mass, a measure of inertia. This is I, which is a measure of your rotational inertia. V, how fast you're moving. Omega, boom, how fast you're spinning. So they're both a similar type form. Yeah. Now, on all of these, if you look at this one, you have kilograms times meters per second squared, which gives you kilograms meters squared over second squared, otherwise known as Newton meters. Okay, because newtons are kilograms meters per second squared times meters, which gives you kilograms meters squared over second squared, which gives you
We don't know.
joules. Okay? So, oddly enough, kinetic energy is measured in joules. Now, rotational kinetic energy, what's I measured in?
LW. LR.
How about kilograms meters squared? Because it's mr squared, right?
Can be.
Then you have omega, which is measured in,
Radians per second.
but that gets squared, we drop out the radians, so we get kilograms meters squared over second squared, which is the exact same.
As
Joules.
Okay?
crazy.
Now, look at Einstein's equation of relativity. This is the short version.
Alright.
You have E equals mc squared. What's the M? Mass, measured in. C is what?
Meters squared over second squared.
The speed of light, right? So it's meters squared over second squared times kilograms, which gives you the exact same thing here as translational kinetic energy. It's the exact same thing as rotational kinetic
Energy.
energy.
Wait, so
E equals energy.
if you
Just
take
that
the
part.
mass of something and multiply it by the speed of light squared.
But that's if you change that mass into pure energy. So like this works, like our sun works right now because hydrogen is being converted into helium. And in the process, the helium has slightly less mass than the hydrogen that you start with. So this is the mass lost in a nuclear reaction. So yeah, if I plug in your mass and I can change you into pure energy, this is how much energy that you could produce. If I changed you, we could. If we could take, you know,
One of them would be like,
if you're willing to make the sacrifice, the problem is, how do you get into pure energy?
Only one person, that'll change.
really?
Okay.
And it would
I hope they
very
don't come up with a
physically
way to
smart.
do that.
Got this. Now, so let's talk.
Yep.
You go to Harvard.
You can honestly have a person
So M's going to be what?
Math.
Kilograms. G,
Meters per second squared.
H.
Meters.
So guess what? You get
Kilograms, meters.
kilograms meters squared over.
Speed of light times mass. Squared.
Now,
Equals joules.
so
Hey,
here's the
Mr.
deal.
Mr. Baker,
What?
have you heard about the tidal energy?
Oh yeah, Australia's doing it.
Yeah.
It's cool. Okay, so let's talk kinetic energy. So if I take this golf ball and throw it up in the air, does it have a certain amount of kinetic energy while it's in the air? Yes. Why?
Because it's got velocity and it's got a mass.
Yeah, it's got velocity and has a mass. So here's the question. Is kinetic energy a vector quantity or a scalar quantity?
I don't know.
It's a
It's a
vector
vector.
because it has direction.
Vector?
Hey,
This has velocity.
Everybody cool with vector? Has a direction?
I thought
I feel like one day he's gonna do that.
vector.
So here's the deal. On the way up, my kinetic energy is 1/2 m times some velocity squared, right? True?
Yes.
Okay. On the way
No,
down,
it doesn't.
I'm going to have 1/2 mass times a negative velocity
It
squared.
doesn't have. Oh, that's crazy.
I told you guys.
So therefore, kinetic energy can never be
Vector.
a negative number. Therefore, it is a
Scalar.
It's a scalar.
I told you guys.
So
It's a scalar.
We all need to stop talking.
when it has energy, it's just a certain amount of energy. I don't have energy in a particular direction. Momentum I have in a particular direction. I don't have kinetic energy in a particular direction. So, let's go down to the library and we'll look at how energy...
Oh, he's sweet.
Are you recording? Okay. So what I'm going to do... Here, watch out. I need my space. Okay? So I'm going to pull it up here and then I'm going to let go of it. So, when I lift it up, am I doing work?
Yeah.
Yes, because I'm storing
Energy.
what kind?
Potential.
What kind of potential? It's either gravitational or a spring.
Gravitational.
Yeah, there's no spring involved. I'm not pushing it against a spring, right? Now, when I let go of it, when I calculate the energy that I'm going to store, it's going to be the difference between this point and where it ends up over here. So the path that it takes, whether I swing it up like this, or if I just lift it up to that height, doesn't make any difference. I'm still going to do the same amount of work. I'm still going to do the same amount of potential energy. So I'm going to hold it up here, like this. Okay? And then,
Oh my gosh.
okay. Oh, the very first time, yeah, it did. Okay? Now, why did I know I'd be okay? Because I'm a physicist.
Conservation of energy.
Well, here's the deal. Could it gain energy through the process to swing higher than when I let go of it?
No.
No. Now, if Ham over there pushes it, then I'm going to duck. Okay? So as long as there's no other source of energy, when this thing is let go, there's only a certain amount of energy that's in the system. Okay?
It
Oh,
was
yeah.
right there.
Yeah, the very first time I did this, it was like, I'm not filming this because if it goes south, ooh, don't want that on tape. So, when I let go, we're all potential energy, right? Then when it gets down here, it's all kinetic. Now, is it going to have a certain velocity at the bottom? Yes. Because I only had a certain amount of potential energy up there, so I only have a certain amount of kinetic energy here. Now, if I just hold it up and I just drop it, would it hit with the same velocity here as if it swings in an arc?
Yeah.
Yes. Why?
If you threw it up, you think all of them just come down.
Because it has the same acceleration. I'm bowling ball.
Doesn't have the same acceleration.
Because that's the same work.
Why doesn't it have the same acceleration?
Because up here, look at the time, okay? If I just drop it, your acceleration is 9.8. That won't take very much time. Over here, the acceleration is much less, okay? Because of the fact that it's going to take a lot longer to get to that point. But here, you can visualize this as being like a container. So when I have it up here, my container is full of ooey, and there's no kinetic energy. So whether it goes from here straight down, or if it swings in an arc, I only start with so much potential energy. So I can only have so much kinetic energy in the system. Now, if I push it, I'm not going to do that. I won't stand here either. Because even if when I do this, I have to make sure that I only let go of it. Because if I push it, then I'm adding kinetic energy to the potential energy, and bad things are going to happen. But if I just stand here like this, and do nothing but just let go of it, then
From this angle, it looks like it's going to hit you.
So that's why I know that I'm good, because, and as a matter of fact, what's going to happen over a period of time?
Okay, stop.
Yeah, because then I'm looped out. Here's the deal. However much energy that I have is the same throughout the system. All I'm doing is changing its form. So this energy still exists in the room, but it's the thermal energy and vibrations of the molecules created by the friction width as it goes through. Okay? Beautiful. Brilliant. Got it. So.
Oh, I'm sorry.
Moments with Kendra.
Moments with Kendra. Hello, class.
Okay. So, right now, what type of energy does the ball have?
Potential.
What?
And kinetic.
What?
No kidding.
We're spinning on this earth, so.
If you look at the kinetic energy as this ball being on the spinning rock, the ball has kinetic energy.
We all do.
Okay, we all do. But within the frame of reference of the room, the ball only has UG, right? We only have UG, MGH.
How do you calculate potential? Okay, here it is. Oh, there it is too.
Yeah. Okay. So here's the question. Is it possible for an object to have both gravitational potential energy and translational kinetic energy at the same time?
Wait, what?
Can you have UG, gravitational potential energy, and translational kinetic energy at the same time?
Transitional?
Yeah.
Yeah, you can. Yes.
Transitional or translation?
Yes, and look, if I move it like this, does it still have UG?
Yeah.
Yes. But it's, because it's above the ground, right? And it has motion, so therefore it has translational kinetic energy. So, Miss Softball, I'm going to throw this to you.
Okay.
Okay? So I'm going to throw it. You ready? Okay.
You won.
Now,
Rocket back.
when I threw it, did I do work?
Yeah.
Because I exerted
have
force
strawberry
through
hands
A distance
a
step.
distance. Did Mara do work when she caught it?
Yeah. I think somewhat.
It's my
maybe
favorite. I
her
love
angels
strawberries. You can have some.
Yeah. So,
You can eat it.
did you change the kinetic energy of the ball? Yes. So you did work on it. Now, throw it back. Okay, now, if I don't catch it, okay?
They throw it back.
He's just like, no.
Yeah.
He just holds it.
And then I'll just kind of definitely do this. Now, I didn't do any work on it because I didn't exert a force. So therefore, the kinetic energy did not change.
Until it hit the wall.
You
So,
would do work even if you just stopped it?
yeah, because there's got to be a certain amount of compression. So there's going to be a certain amount of distance.
What's the other?
So here's the great equalizer out of this deal. So work will always equal your change in energy. Okay? Well, now that might be change in UG. Like if I lift Hank up, it could be a change in kinetic energy. So like if you stop it, it could be a change in rotational energy if I take that bicycle wheel to make it spin. It could be a change in us if I take a spring and compress it. If once you get into electrical fields, you can have a change in OOI. Like if I take two electrons that don't want to be near each other and I push them together, I have to do work to push those electrons together. So any work can be a change in any of these. Now, here's where this is going to get a little bit weird.
What's USB?
Huh?
What's USB?
Is it the spring?
Yeah.
That's the energy of a spring. Okay? So all of these can be written as whatever type of energy it is minus your initial. So if you want to change in UG, that's UG minus UG naught. If it's changing rotation, translational kinetic energy, it's KT minus KT naught. So what you will see is that a lot of times your work and your change in energy are going to be the same number. So if you get the same answer 2 or 3 times in a row, it's cool. Don't worry about it. Because now we're going to be setting so many things equal to each other. So let's say, for example, I generate a force distance graph that looks like this. So let's say this is 10 newtons and this is 2 meters. Got to find the area?
Yeah.
Yeah. What would the area be?
Force distance, that is work.
Joules.
That is joules.
Which would be the work done, right? So, this could be me lifting a ball. I have to exert 10 newtons to lift up an object 2 meters. Okay, that's the work that I would do. This might be a car starting at rest, and I know the engine can produce 10 newtons of forward force, and it's going to be exerted over 2 meters. I might have 2 electrons a certain distance apart, and I'm going to push them together. This is the force that I have to exert to push these charged particles together. Doesn't make any difference, okay? Literally, does not make any difference. So if I exert this force over a longer distance, what's going to happen to my work? Bigger or smaller?
Bigger.
Bigger. So if I exert the same force over a longer distance, I do more work, therefore I change more energy. Same thing is true of your car, okay? You get in your car and you press down on the gas pedal. You're exerting a force over a certain distance that your car is going to travel. If you press down on that gas pedal and you just hold it there while the car travels just a short distance, you don't do much work, your energy doesn't change very much. Whereas if you press down on that gas pedal and you hold it there while the car travels a great distance, you're going to change the energy a lot. Okay? But don't confuse this with a force time graph. Okay? Because force time graph creates change in momentum. Force distance graph gets you work. Okay? So don't confuse the two. They're related, but nary the two shall meet. Now, when Mara threw that ball back, did I do any work on it? No. So the area of the graph is 0. So how much did the ball's energy change? Good. So just like if there's no force over no time, you don't get a change in momentum. If there's no force acting over a distance, you don't get a change in energy.
What does Henry calculate?
Henrys are magnetic fields, I'm pretty sure.
So if we're all attracted to each other in a gravitational sort of way, then aren't we all doing work right this second?
What?
Only if I move towards you in a gravitational kind of way.
The ball kept on moving away from you.
So again, to do work, there's 2 things. The force there has to be movement in that direction. So if I move away from you, okay, I'm in the opposite direction.
So if I move towards you at all, then I'm doing work towards you.
A little bit.
Yeah.
But don't take that, no. And don't use that as a pickup line. Okay?
I'm doing some.
Hey, baby, I'm about to put in some work.
Hey, I'm just trying to do some work.
Let me see that. Let me see that, please. Ma'am, can I see that, please? Hi, name's Reese. Can I see that?
I'm so confused. What?
Hi, name's Reese. May I please see that?
She said,
Get thrown in a circle.
This video.
Oh, I kind of forgot about that. I always forget that thing.
Prairie kittens.
So, let's say that you've got a little toy car with a mass of 10 kilograms. It starts off at 0 meters per second. At some point later, it's traveling 6 meters per second. Did the kinetic energy change?
Yes.
Yes. Why?
Because it was at 0 and now
It
it's
was at 0 and now we're moving, right? So, can I find the kinetic energy at this point? Yeah.
half.
1/2 times 10.
mv squared, right? So I'm going to have 1/2 times 10 kilograms times 6 meters per second squared.
So you always use the
36
final.
times
36, half of
180.
36 is
180.
18. 18 times 10, I get 180 joules of energy. Now, what if I double the velocity to 12? Will that double my kinetic
No,
energy?
it'd be
Well,
done.
it's 4.
What did
Four.
you just
Enter it?
4 times.
4, why?
Because it's squared.
Because it's squared. So if I double,
Yep.
if I double my velocity, I quadruple my kinetic energy. But if I double my velocity, what happens to my momentum? Okay, right now I have a momentum of 60, right? If I double the velocity to 12, my momentum just becomes, just doubles, because momentum is just mass times velocity. So if you double velocity, you just double momentum. But if you double velocity, you quadruple the kinetic energy. No, I was asking about the momentum. Okay. Now, at this point, do I have enough information to calculate the work that was done?
Work equals.
Quadruple
Wait.
what?
If I double the velocity, I quadruple the energy.
Wait, yes, you
Yeah.
have it right
Force
here.
times distance.
Because you have,
That's the work.
because you have the change in energy.
Work
Yeah, so
equals
work equals
force times displacement.
It's right there.
force times distance, it also equals change in energy.
Why?
What was my initial kinetic energy?
0.
What's my final kinetic energy?
6. So you take 6
180.
minus 0.
So my final kinetic energy is 180. 180 minus 0,
Oh,
I get...
energy.
Why do we do that?
It'd just be 180 times.
No, it's just
No,
being
just
straight.
why do we do that?
So the work that's done is my change in energy. Same number. Now, at this point, do I have enough information to calculate the force?
Ooh, no, because
No.
you don't have a distance.
I don't have a distance. Now, if I say that happened over a distance of 2 meters,
Boom, we got
Man,
it.
heck yeah.
then I can
Force.
do,
180
Work
divided by
times
2.
divided
Yeah.
by.
Yeah.
and it would be 90 meters of force. Because if work equals force times distance, if my distance is 2 meters, 180 divided by 2, I would get 90 newtons of force. Now, what if I went through the exact same change in velocity, but instead of doing that at 2 meters, I did that in 10 meters? What's that going to do to the amount of work that's done?
Decrease.
Nothing. It won't change the amount of work that's done. Why? Because I'm still going to go from 0
Oh,
to
that's
6.
Your mass is-
So my change in
That is
kinetic energy
crazy.
is going to be the exact same number. But what's going to happen? What's going to happen to my force? Force is going to go way down. Think about this when you drive your car. If you go out here on 119th headed south and you're driving like an idiot, oh, I'm going to press down on the gas, right? Okay? You exert a large force over a small distance to get to the speed limit, which you're not going to drive anyway, but I'm going to be nice. Versus, hey, I'm going to drive rationally I'm going to exert a smaller force over a longer distance to have the same change in kinetic energy. Okay? And momentum. But that's a function of time. So, it's the same idea though. As time gets bigger, or as force gets bigger, excuse me, or as force or distance gets bigger, you require less and less force. Okay, so let me kind of get you through these.
Energetic energy.
When you get to question number 4, where's the potential energy of an earthquake stored? Which used to be, until about 5 years ago, was this, academic idea in Kansas, oh, it's an earthquake, oh, whatever. And now it's like, pretty regular occurrence. So where is the energy stored?
In the ground.
Yeah, well, you're on the plate boundary. So basically, when you have an earthquake, what's happening? Blank energy is changed into kinetic. Okay? So like the last one happened, a couple weeks ago? Tweeted out, seismic energy.
Oh yeah.
Potential energy was changed into kinetic energy via a seismic wave.
So I'm like, I kind of don't believe in the whole
Does it take time to play?
People say that it's fracking.
Is it cyclic?
It isn't the fracking.
Yeah.
It's the water that's injected
Yeah.
to dispose of it. That's what, the fracking isn't.
Yeah, but
So,
people are saying like,
hold
it's
on.
fracking.
Hold on.
So is that just
So when you get to number 13, with the tennis ball, you have to go old school to find the velocity.
You said number 13?
Yes.
Go old school?
So you can either go old school, force time, change in momentum. If you really want to go old school, you can go F equals ma. Okay? Right?
Wow.
I'm just telling you. On number 14, do not be surprised if you get the same answer quite a few times, because you're talking about work and changing kinetic energy and the final kinetic energy. So you might get the same answer on number 14. Not all of them will be the same answer. Don't think, oh, I found the 14th answer to A. I just write that down. But you are going to get a lot of the same answers. So, okay, I'm done. You're on your own.
Letter